Today's big overarching concept is that of the mole. Now, the mole is our basic unit of counting in chemistry. We kind of use the mole the way that a baker uses a dozen. It's a method of counting large quantities of objects into a smaller quantity. Instead of counting up 12 donuts, they sell you 1 dozen donuts. Instead of counting up 144 cupcakes, they give you 12 dozen or 1 gross of cupcakes. It's the same kind of concept overall, fundamentally. The only difference is that it is a massive scale change by comparison. The chemical mole is equal to Avogadro's number of objects, 6.022 times 10 to the 23rd. Now, the nice thing about the mole is that almost every other way that we can characterize things comes back to that concept as well. So we made mention before of the concept of molar mass, or at least atomic mass on the periodic table, using the masses on the periodic table to tell us how much an atom weighs, or how much a molecule weighs, or how much a fundamental unit of a crystal, an ionic compound, weighs. Well, all of those concepts that are on the micro scale for AMUs, when we bring it out to the macro scale of grams, they all become relative to the mole as well. So those values that we got off of the periodic table for atomic masses, molecular masses, formula masses, can all become molar masses if we simply change the AMUs to grams. And so we introduce in that video online a couple of different ways of doing conversions. So if we are looking at the particulate world, if I have a number of particles of a substance, and I want to convert that to moles, I'm going to use Avogadro's number as a conversion factor to do so. And so if I want to go from particles to moles, I use the top conversion. If I wanted to go from moles to particles, I'd use the bottom conversion. Really, the only difference between them is whether we multiply or we divide. But there's some other things that we can do as well. Again, bringing up the concept of the molar mass, using our periodic table to tell us masses in grams instead of masses in AMUs. And we can kind of summarize all of the different kinds of calculations that we can do with this. This graphic here shows us all of the different combinations of calculations that are possible. And what's interesting about this particular graphic is, yes, we get specifics on if I'm going from mass of a compound to moles of a compound, then I'm going to want to divide by the molar mass of the substance. All these little configurations can be linked together in a string of calculations in the same kind of way that we did unit conversions at the end of chapter 1. Because all of these are simply conversions. Molar mass says that 1 mole of a substance is equal to X number of grams of that substance, a conversion factor. Avogadro's number says that 1 mole of the substance is equal to Avogadro's number of particles of that substance. The chemical formula of a substance gives us a ratio between one element and another element in that compound. It also tells us that for every molecule of that substance, we'll get a certain number of atoms of an element. So for example, if I have propane, C3H8, my chemical formula tells me that one molecule of C3H8 is equal to 3 carbon atoms and 8 hydrogen atoms. And if I extrapolate that, that means that 1 mole of propane is equal to 3 moles of carbon and 8 moles of hydrogen. So this little infographic here does give us a lot of information, a lot of context that we can use. And we can almost think of this as a map. Now, those of you that have had me in lecture before, you know I like this map concept when it comes to calculations of this kind, because it becomes something very visual that you can draw, where I can say, look, I want to go from mass of a substance to atoms of an element in that substance. And all I need to do is kind of draw a series of arrows that point me from my starting location to my ending location. And if I go through that, I can see I'm going to need 1, 2, 3 calculations in total to get from point A to point B. So I'm very big on this, and you'll see similar maps of these kinds as we progress through the semester, because again, it's a very visual kind of way of looking at calculations. And when we get to stoichiometry in chapter 7, it's going to be very easy to take this picture and move it over to stoichiometry, which has a very similar kind of picture, a very similar kind of pattern to it. So let's move off of this. Again, if you want me to see me do the examples that are in that PowerPoint, I go through each of those examples in the video that's on YouTube. Instead, what I want to do is I've pulled some resources online, and we're going to actually go through those instead, just to give us some new things to work on. So let's do a couple together, and then I'll stop talking for a few minutes, let you work on a couple on your own. I'll stop by and check on each of you and see how we're doing. So let's start off with a relatively simple one. How many moles are in 22 grams of argon? Now again, if we go from point A to point B, what we are going to see is that this map concept is going to show up in a number of ways along the way. So in this particular example, we want just a relatively simple conversion. We're going from a mass of a compound down to moles of a compound. We can see that those two are linked together. It's a one-step conversion. This one should be relatively easy to work on and do. So the concept that we go after here is I have 22 grams of argon, AR. I need to convert those grams of argon into moles of argon. According to the periodic table, there are 39.95 grams of argon in every mole. So my grams of argon cancel. 22 divided by 39.95 to two significant figures, because I only started with the 2, is 0.55 moles of argon. Right? So this one's relatively simple and straightforward. We just had a one-step conversion that we had to do. We went ahead and did it. Any questions or concerns with this particular example? Okay. All right, let's pivot then. All right. How many moles are in 68 grams of copper 2 hydroxide? Okay, if we go back to our mole map here, this time, again, we are going from mass of a compound to moles of a compound. Again, it's going to be a one-step kind of conversion. We have 68 grams of copper 2 hydroxide, CuOH, taken twice. Again, we're going to convert our grams into moles. Molar mass of copper 2 hydroxide, I have to figure out. Copper is 63.55. Oxygen is 16. But there are 2 of those oxygens, because oxygen is contained in those parentheses. So 16 times 2. And there are 2 hydrogens. Hydrogen is 1.01, multiply that by 2. We get a total mass of 97.57 grams in 1 mole. 68 divided by 97.57. to two significant figures again is 0.70 moles of copper 2 hydroxide. So again, very, very little here that is new. This is just a slightly more complicated example because we had a compound instead of an element. All right, let's kick this up a little bit because these particular calculations are a little bit simple. Any questions before we kind of move off of it? All right, so let's go to our whiteboard then. And let's do some examples that are a little bit more rigorous. Get rid of that. Okay. How many carbon atoms are in 0.254 moles of sodium oxalate? Now, if we follow our map along here, you'll see that we are starting with moles of sodium oxalate. We are going to have to turn that either into moles of carbon or molecules of sodium oxalate, either way. And then we're going to turn that into atoms of carbon. So this is a two-step conversion here. Now, these kinds of conversions don't get more complicated than 3 steps. Because if you look at that map, any 2 of these boxes are going to be connected by, at most, 3 sets of arrows. If I go from one corner to the other, that's going to be a 3-step calculation. Otherwise, there are only going to be 1 or 2 steps. But if we start with our moles of sodium oxalate, our first step is to convert that into moles of carbon. So I want to turn moles of sodium oxalate into moles of carbon. For this, I'm going to need to use the chemical formula. Every single molecule of sodium oxalate has how many carbons in it? 2. So the thing to keep in mind here is that if the ratio works at the molecular level, it's going to work at the molar level as well. So if one molecule has 2 sodiums, 2 carbons, 4 oxygens, then 1 mole is going to have 2 sodiums, 2 carbons, 4 oxygens. And I can even put those against each other if I wanted to. If I knew how many atoms of oxygen there were, I could use that ratio, 4 oxygens to 2 carbons, to figure out how many carbon atoms there were. So my moles of sodium oxalate go away. I now have moles of carbon. I need to turn that into atoms of carbon. So I've got moles of carbon in the denominator, atoms of carbon in the numerator. My moles cancel. Here's where Avogadro's number comes in. 6.022 times 10 to the 23rd for every mole. Now, before we go about solving this, a word of warning here about scientific notation and your calculator. Depending upon what model of calculator you have, you're going to have different instructional steps for entering your scientific notation. The thing that I want to avoid you doing, regardless of what it is, do not try to enter this number as if it was a mathematical function, meaning 6.022 times 10 to the 23rd should not be entered in as 6.022 multiplied by 10 to the 23rd. We don't want that function to be put in, because here's the problem. As it's written right now, it's not that big of a deal because Avogadro's number happens to be in the numerator. But if this is in the denominator, what you're telling the calculator to do is to divide by 6.022 and then multiply by 10 to the 23rd. You'll end up getting the wrong answer, at least from an exponential standpoint. Now, every calculator that is at least a scientific calculator, so no four-function calculators, but any scientific or graphing calculator is going to have one of two buttons that will do scientific notation for you. And I'll try to show you what those look like. This one. Okay. I happen to have a Casio. My scientific notation button is this one right here. It's the exponential button. If you have a Casio, you'll probably find your button very similar in placement to mine. It might say 10 to the on it. But it'll be right here near the period. All right. Ben, do you have a TI? Yeah. All right. Can I borrow you for just a second? Okay. Most Texas Instruments look like this in some kind of way, scientific or graphing alike. The button you want to hit here is this EE button. So for most of you, it is a secondary function. So if you hit second, comma in this case, it'll give you that little uppercase E. That is your scientific notation. This is going to save you keystrokes first and foremost, but it's also going to make sure that the number that you put in is going to be calculated properly. So again, if you put in 6.022 times 10 to the 23rd, it's going to take that 6.022 and multiply by 10 to the 23rd. Again, doesn't matter so much if your Avogadro's number is in the numerator, but it matters a heck of a lot if it's in the denominator. So back to the matter at hand here. We're doing our calculation. 0.254 multiplied by 2 multiplied by Avogadro's number to 3 significant figures will give us 3.06 times 10 to the 23rd atoms of carbon. Really good check for these kinds of calculations. If you are trying to figure out the number of particles that are present, your answer should be big. If you are trying to figure out the number of moles, the number of grams, by comparison, your answer should be relatively small. Now, it's not to say that occasionally you don't get answers in the thousands or 10,000s or even a million. But compared to 10 to the 23rd, that's a small number. Because that's only like 10 to the 4th, 10 to the 5th, 10 to the 6th. If you're dealing in moles and grams, your numbers are generally going to either be low fraction of decimals or numbers in the tens, hundreds, maybe even thousands. If you're dealing with particles, you better be finding exponentials. Your calculator is either going to generate a giant number or it's going to automatically convert it to scientific notation for you. And that's what you want to see. Now, the only caveat on that is in those rare circumstances where you're asked how many moles are in, how many moles is 3 particles, then yeah, you're getting a small exponential number in that case. Those are kind of rare, and you'd expect that to be small. All right, any questions with this one? All right, it's your turn to impress me. I'm going to give you 2 questions to work on, and then we'll kind of come back at the end and talk about them. I'll come around and see how everybody's doing. So there's your first one. Determine the number of nitrogen atoms in 39.99 grams of ammonia. Here's your second one. Right. See what you can do with those 2, and then about 10 minutes or so, we'll come back and wrap up and talk about it. Let's look at them each individually here. So the attack strategy for the first one, I've got to take that grams of ammonia and turn it into moles. And then that's moles of ammonia. And then I'm going to take those moles of ammonia and turn them into moles of nitrogen. And finally into atoms. So my first step, 39.99 grams. I need to turn the grams of ammonia into moles. Way to do that is molar mass. Molar mass of ammonia, 1 nitrogen plus 3 hydrogens is 17.04 grams per mole. My grams of ammonia cancel. Now I need to turn the moles of ammonia into moles of nitrogen. That information is going to come from the chemical formula itself. Every ammonia molecule has one nitrogen in it. Last step, I need to turn the moles of nitrogen into nitrogen atoms. Avogadro's number of nitrogen atoms in every mole. My moles cancel. To 4 significant figures, 39.99 multiplied by Avogadro's number divided by 17.04, 1.413 times 10 to the 24 atoms of nitrogen. For the second one, this one's a little bit trickier, but the guts of it are pretty close to the same. I'm going to have carbon atoms that I'm going to turn into oxygen atoms, which I can then turn into moles of oxygen, and then finally grams. So starting with 2.33 times 10 to the 21st carbon atoms, my first step is to turn the carbon atoms into oxygen atoms. And where that comes from is our chemical formula. Our chemical formula tells us that every carbon is matched by 2 oxygens. My carbon atoms cancel. I now have oxygen atoms. From here, it follows pretty closely to the map. So that was the only wrinkle that we really didn't discuss at all. But from there, I can go Avogadro's number of oxygen atoms in 1 mole, and 1 mole of oxygen is 16.00 grams. Now, some of you may be saying to yourself, why not 32 there for the oxygen? Got to remember, that's the molar mass of molecular oxygen, O2. Here we're talking about atomic oxygen, so it's just 1 oxygen atom. It's 16. 2.33 times 10 to the 21st, multiplied by 2, multiplied by 16, divided by Avogadro's number. Here's where that exponent key comes in real handy. To 3 significant figures, 0.124 grams of oxygen. So not a terribly large amount of oxygen in that sample, but we didn't have a whole lot of carbon dioxide there either. But again, numbers should make sense. We're talking about a mass. Our mass value here, relatively low. It's a decimal. It's not extremely high. It's not extremely low. Contextually, it makes sense. Masses in grams should be relatively low numbers. Not super high, not super low in either direction.